Right now, something is moving through our solar system that shouldn't exist. And in exactly 67 days, we're going to find out what it really is. It's been 8,000 years since this object entered the Oort cloud, that frozen graveyard of ice and rock 15 trillion kilometers from the sun, so far away that light takes over a year and a half just to cross that distance. For 8 millennia, it's been falling toward our star, accelerating, getting closer. But now it's reached the turning point. Now it's heading back out into the void. And that's when the impossible began. When you track an object in space, the math is simple. Gravity pulls, momentum carries, and we can predict where something will be years in advance down to the meter. We've been doing this for centuries. The equations never lie. Except this time they do. This object, designated 3I/ATLS, the third confirmed interstellar visitor ever detected, is accelerating in ways that gravity alone cannot explain. Something is pushing it, something we can't see. Non-gravitational acceleration. That's what astronomers call it when they don't want to say what they're really thinking. Sure, comets do this near the sun. Ice heats up, gas jets out, creating thrust. Basic rocket physics. But 3I/ATLS is out in the Oort cloud, where temperatures hover just above absolute zero, where ice doesn't sublimate, where there shouldn't be any thrust at all. And yet, it's accelerating. Persistently, measurably, enough that if we don't include this mysterious force in our calculations, our predictions miss by millions of kilometers. Let that sink in. We're watching an object that breaks the rules. Either everything we know about how ice behaves in deep space is fundamentally wrong, or we're looking at something that doesn't fit into any category we've ever created. The first interstellar visitor was Oumuamua in 2017, that strange cigar-shaped object that tumbled through our solar system and sparked 1,000 conspiracy theories. The second was 2I/Borisov in 2019, which behaved exactly like a normal comet, tail and all, boring and predictable. But 3I/ATLS, detected by the Atlas survey system scanning for killer asteroids, has been different from the moment we found it. Its orbit screamed interstellar, a hyperbolic trajectory that proved it came from beyond our sun's influence. But that acceleration, that unexplainable push, has been there from the beginning. Real, persistent, impossible to ignore. And now it's heading toward Jupiter. Not just near Jupiter, toward Jupiter with an accuracy that makes your skin crawl. March 16th, 2026. Mark that date. In 67 days, 3I/ATLS will pass within 53.61 million kilometers of Jupiter. That sounds far, right? It's 140 times the distance from Earth to the Moon. Vast, safe. Except it's not, because Jupiter has what's called a hill sphere, the region where the planet's gravity dominates over the sun's pull. That sphere extends to 53.5 million kilometers from Jupiter's center. Now do the math. 3I/ATLS will pass at 53.61 million kilometers. That's just 110,000 kilometers outside Jupiter's gravitational dominance zone, a difference of 0.2%. This interstellar object is threading a needle with Swiss watch precision. Random encounters don't work like this. When something comes screaming in from deep space on a hyperbolic trajectory, the odds of passing this close to any planet are microscopic. The solar system is mostly empty space. Yet here comes 3I/ATLS with its unexplained acceleration, arriving at Jupiter's doorstep at exactly the right distance, exactly the right time, moving at exactly the right speed. But wait, it gets worse. One day later, March 17th, 3I/ATLS will pass within 30.46 million kilometers of a moon you've never heard of, Eupheme, just 2 kilometers across, one of 95 moons orbiting Jupiter, discovered in 2003. A tiny captured rock in the Ananke group, 15 moons on wildly elliptical retrograde orbits, the shattered remnants of something larger that Jupiter captured and destroyed long ago. Euphori's orbit takes 588 days. Because it's so elongated, the moon's distance from Jupiter swings wildly. At its farthest point, Euphore reaches 27.7 million kilometers from Jupiter. And here's what should make your blood run cold. Euphore will reach that farthest point, its apogee, on January 23, 2026, just 15 days from now. And 52 days after that, 3I/ATLS arrives. When Euphore is at its most distant point, it's barely held by Jupiter's gravity, moving slowly, vulnerable, at the edge of stability. And that's precisely when 3I/ATLS shows up. It's like the interstellar visitor scheduled an appointment.
Now, astronomers will tell you this is coincidence. Jupiter has 95 moons. With that many objects moving around, something's always in an interesting position. Probability, statistics, cosmic lottery. Except Oumuamua didn't do this. 2I Borisov didn't do this. Those were flybys, brief glimpses before they vanished forever. But 3I Atlas is engaging with our solar system in ways previous visitors never did. That unexplained acceleration means its trajectory has been modified by something we don't understand. And now it's arriving at Jupiter at the exact distance and exact timing that puts it right at the threshold of capture dynamics. When 3I Atlas passes Jupiter on March 16th, it'll be moving at 66 kilometers per second relative to the planet. That's nearly 240,000 kilometers per hour, fast enough to cross the United States in 60 seconds. At that speed and distance, Jupiter's immense gravity will bend 3I Atlas's path, stress the object, create conditions where very interesting things can happen. Violent things, transformative things. Things that might add to Jupiter's collection of 95 moons. Euphore wasn't always alone. None of the Ananke group moons were. They're fragments of a single parent body that wandered too close to Jupiter in the ancient past. The planet's gravity captured it, tore it apart, scattered the pieces into those chaotic retrograde orbits. The largest fragment became Ananke. The smaller pieces became 14 other moons, including Euphore. These are the orbits of violence, capture, destruction. And Jupiter's very good at this. In the year 2000, we knew of 17 Jovian moons. Today, 95. There are likely many more waiting to be discovered, too small and dark for our current telescopes. Jupiter is a gravitational trap, constantly snaring objects that wander too close. So the question becomes unavoidable. Is 3I Atlas about to be captured? Could fragments break off during the encounter and end up in orbit around Jupiter? Could we wake up on March 17th to discover Jupiter has a 96th moon, one that came from interstellar space? Here's where the physics gets uncomfortable, deeply, mathematically uncomfortable. For a fragment of 3I Atlas to become bound to Jupiter, it needs to slow down dramatically. At a distance of 53.61 million kilometers, Jupiter's escape velocity is 2.2 kilometers per second. Anything moving slower than that can't escape. But 3I Atlas will be moving at 66 kilometers per second relative to Jupiter. For a fragment to transition from 66 to less than 2.2, it needs a velocity change of at least 63.8 kilometers per second. And not just any direction. The kick has to cancel most of the motion while leaving enough tangential velocity to maintain orbit, instead of just falling straight into Jupiter. This is exquisitely fine-tuned, surgical precision at cosmic scale. Can a natural comet produce velocity kicks of 63.8 kilometers per second? Let's look at the mechanisms. When comets outgas, the velocity of ejected material is limited by molecular speeds at comet temperatures. For water ice, that's hundreds of meters per second, maybe a kilometer per second at most. We're off by a factor of more than 60. What about tidal breakup? In 1994, comet Shoemaker-Levy 9 was ripped apart by Jupiter's tidal forces before smashing into the planet. But tidal forces don't fling fragments at high speed. They gently pull things apart. The velocity differences are meters per second, maybe hundreds, not tens of kilometers per second. Jupiter's surface escape velocity is 60 kilometers per second. Any breakup process on a much smaller body like a comet cannot impart velocities exceeding what a massive planet can generate. The energies involved in shattering a kilometer-scale object simply don't allow for it. The physics says no, emphatically. And remember, the escape velocity at 3I Atlas's closest approach is only 2.2 kilometers per second. The fragment's velocity has to land in a razor-thin window between 0 and 2.2. That's a tolerance of roughly 3%. In engineering, we'd call this precision manufacturing. So here's what we're facing. If on March 17, 2026, we observe a new moon around Jupiter that originated from 3I Atlas, we will have witnessed an outcome that natural physics says is impossible. The creation of a bound satellite from a high-speed interstellar encounter requires velocity changes that comets cannot produce through any known mechanism. That would be a technological signature. Evidence that 3I Atlas can control its fragmentation, impart specific velocities to specific pieces, execute maneuvers that natural objects cannot perform. Evidence of design. Evidence of intention. Evidence that we are not alone. Let me be absolutely clear. We are not saying 3I Atlas is artificial. Not yet. What we're saying is this. If we observe certain specific outcomes from the March encounter, those outcomes will be nearly impossible to explain using natural processes alone. They would require new physics we haven't discovered, or they would require us to consider possibilities we've spent centuries dismissing. March 16, 2026 is 67 days away, and the world's most powerful instruments are already turning toward Jupiter. NASA's Juno spacecraft has been orbiting Jupiter since 2016. During the encounter, Juno will have a front-row seat with cameras, spectrometers, and sensors that can characterize objects with resolution no Earth-based telescope can match. From the ground, the Atacama Large Millimeter Array in Chile, the Very Large Telescope, Keck Observatory, Subaru Telescope in Hawaii, all will be watching. Coordination between observatories will ensure continuous coverage, multiple independent datasets, no gaps in observation. Optical tracking will monitor 3I Atlas's position and brightness. Any fragmentation will produce brightness changes. Spectroscopy will analyze ejected material, searching for ice, rock, organics, or something more exotic. Infrared will hunt for thermal emissions. Radar will provide direct ranging and velocity measurements. But the critical observation is simple. After March 17th, will there be new objects orbiting Jupiter that weren't there before? Detection won't be instant. Even after fragments enter bound orbits, it takes time to confirm their presence, calculate trajectories, rule out pre-existing objects we simply hadn't noticed. We won't have answers on March 17th. The analysis will unfold over weeks, maybe months. But every major telescope with access to Jupiter will be searching. Amateur astronomers with advanced equipment will join the hunt. The data will be public, accessible to the scientific community, allowing independent verification. For a claim this extraordinary, we'll need multiple confirmations from multiple sources. This changes how we think about the search for extraterrestrial intelligence. Traditional SETI focuses on radio signals, optical pulses, electromagnetic signatures from distant stars. But recently, there's been growing interest in artifact SETI, searching for physical objects of extraterrestrial technological origin. Oumuamua sparked intense debate about whether interstellar visitors might be probes rather than rocks. 3I Atlas gives us something better than speculation. It gives us a test. If the object can place fragments into orbit around Jupiter, despite the impossible physics we've discussed, that's not just unusual, that's diagnostic. It's a signature natural processes cannot replicate. Most proposals for finding alien technology involve searching for megastructures around distant stars or listening for deliberate transmissions. But if technological civilizations send probes through the galaxy, watching for anomalous behavior during close planetary encounters might be the most efficient detection method we have. We don't need to search a million stars, we just need to watch what comes to us. Of course, there's a very real chance nothing unusual happens. 3I Atlas might pass Jupiter without incident, continuing its journey until it fades from view.
The non-gravitational acceleration might have a mundane explanation we simply haven't thought of yet. Science is full of mysteries with boring answers. But the possibility remains. The numbers are there, the physics is clear, the timing is perfect, and in 67 days, we'll know. March 16th, 2026, the day an interstellar visitor with impossible acceleration arrives at Jupiter's doorstep with surgical precision. The day we might discover Jupiter's 96th moon. The day we might confirm we've been watching something that shouldn't exist. The telescopes are ready, the spacecraft is positioned, the world is watching. And somewhere out there, 15 trillion kilometers away when it started, 3I Atlas is still accelerating in ways it shouldn't, heading toward an encounter that defies probability, carrying secrets we're about to uncover. 67 days, that's all we have to wait. 67 days until we find out if we're alone in the universe or if something out there has been watching us all along, sending visitors that follow rules we never wrote, executing maneuvers we can't explain, threading needles we didn't know existed. The clock is ticking, Jupiter is waiting, and 3I Atlas is coming.